to go over these different things here, and the first thing I'd like to talk about is the b, which is to do with this particular function here. Now, this is a cos function, but it's got a minus sign in front of it. So let's think about our typical cos function. Our typical cos function, as we know it, is going to start at 1 for the y and then go down to -1, etc. But because this cos function is different, it's got a minus sign, which means it's going to be flipped, which means it's going to start at -1 and it's going to go up and then back down, etc. So it's going to be flipped. It's going to be a mirror image. So if we have a look at our now new cos function, we know that the middle part of any cos function or sine function, if it's just a sine of x or cos of x, is going to be 0. Now this particular cos function is going to be moved up. So instead of being at 0, we've got a new function now, and we need to find out what this new 0 is. What's the new kind of midpoint of this graph? So if we look at the picture, it's really quite easy to see. We are going to be having a look at half of 61.8 plus the 2.7, and that would give you the midpoint of the particular graph. So that's going to be 30.9 plus 2.7. So 30.9 plus 2.7 is going to be 33.6. So that is why the graph has been moved up, and now we are going to have a new d value of 33.6, because d is just to do with how much we shift the graph up and down. Next thing we want to have a look at is the a, because remember we always do it in the order of d, a and b. We've done the d, nice and easy. A is the amplitude. This is just the distance from the midline to the top. This is why it's really good to draw the graph. So the midline we've worked out is going to be 2.7 plus half of 61.8, and there's actually a simpler way of doing it, which we'll talk about in a moment. So 2.7 plus 61.8 is clearly going to be around about 64.5. So we know the absolute maximum of this graph is going to be 64.5, and we know the minimum of this graph in terms of where the Ferris wheel goes is going to be 2.7, because they get on at level 2.7. So this is going to be 64.5, and then this value at the bottom is going to be, as we expected, 2.7. Now the amplitude is simply the distance from the midline to the maximum or the midline to the minimum. So as we already know that the midline is 33.6, or our d value, we're just going to do 64.5 minus 33.6, and that will just give us the answer. Or you could do it the other way around. You could do 33.6 minus 2.7, which is actually arguably a lot easier. So it's going to be 30.9. So what we mean by that is this distance here is going to be 30.9. So we've done the D, we've done the A, and then we've done the B. Now the B is the most complex thing. The B is to do with how many revolutions there are, and it's linked with the periods and things like that. So let's say that B is to do with 360 divided by the number of periods. Now this is a little bit of a complicated question, because we have got this function in terms of time. So we're going to say that within 1.5 minutes, we're going to have a total of 1.5 revolutions. So what we need to decide is how this links to this part of the question. If we're going to have 1.5 revolutions in a minute, because this question is to do with 360 seconds, which is 6 minutes effectively, we need to see, well, how many revolutions are we going to have in 360 seconds? Well, in 60 seconds, we're going to have 1.5 revolutions. So then, therefore, in 360 seconds, we are going to have 6 lots of that, which is going to give us 1.5 times 6, which is going to be 9. So it's all to do with the relationship between the periods and 360. We are going to have 9 full revolutions in 360 seconds, and therefore our B becomes 9. And this is because a normal cos graph or a normal sine graph would have, in 360 degrees, or for this question 360 seconds, it'd have 1 revolution. But we're going to have 9 revolutions, so this is why our B becomes 9. Now, what we'd like to do next is to work out the subsequent questions. So it says calculate the number of revolutions of the Ferris wheel per ride. Now, the ride is for 12 minutes. And this is just a very simple prior knowledge question. All you have to say is that because every minute we have 1.5 revolutions, all we need to do is we take that 1.5 and we multiply it by the 12, and that gives us the answer. So this is why we've got a really simple answer here of 18 revolutions. Now we're going to have a look at part C. For exactly 1 ride on the Ferris wheel, suggest appropriate domain for H. So remember, domain and range are nice and easy things. Domain is just to do with the x values. And the range is just to do with the y values. So from the D, A and B, and from looking at the pictures, the range is probably the easiest of them all, because we can see it ranges from 2.7 to the maximum, which is going to be 61.8 plus 2.7, which is going to be 64.5. So the range is going to be between 64.5, which is the absolute maximum, and 2.7. Hence why we say the range for h of t would be this. Now, rather than just writing h, it should be better to write h of t. Now, in terms of the domain, it says 1 ride of the Ferris wheel. It says a ride on the Ferris wheel lasts for 12 minutes. And we've already decided that it goes round 18 times. So we need to use that information to help us find the answer of this question. At this point, you should have the function, and you should really be able to plot it on your TI-84 calculator. So let's open our TI-84 calculator. Your calculator may look a little bit different to mine, and what we're going to do is we're going to substitute in each of these values. And first of all, we obviously need to make sure it's in degree mode. So we are going to open the calculator, we're going to press mode, and we're going to check it's in degree mode, and then we're going to go into the y equals, we're going to clear what's already there, and we're going to type in this function. We've got minus, we're going to use the small minus at the front, because when we're talking about signs at the front, we always use a small one. And then we're going to write cos of 9x, because our function will be in terms of x on the calculator, plus our d value. Make sure you've cleared it. You've used your small minus, minus a, which is 30.5. 33.9 cos. We need to decide where cos is. It's next to the sine button, which is here. Cos of 9x, because we cannot write it in terms of t. We're going to close the brackets. That's really important here. Plus the d, which is going to be 33.6. Obviously, this might not look right straight away because our window's not quite right. We are going to readjust the window. We want to see more of the y and less of this x. So in terms of seeing more of the y, let's make sure we're at the maximum of the graph. And we said it was roughly around 65. It gets on at 22.7, so 2 is absolutely fine. And let's make this 500. And this might make sense in a moment because we want to see a few revolutions going around. Perhaps this could be a little bit too much, but we'll decide in a moment. So if we want to have a look at the domain for h of t, this is the x values. So it says exactly one ride on the Ferris wheel. So we've said this last 12 minutes, and it's going to be 18 revolutions all together. So we want to find out what happens after 18 revolutions. So how do we do that? Go back to what we were talking about earlier in the sense that if we have a think about this particular function, we know with this particular function how it works is that every minute you're going to have 1.5 revolutions because that says it in the question. So every 60 seconds there was going to be 1.5 revolutions. So we could say 60 seconds is equal to 1.5 revolutions. And another way of thinking about that is, well, how would we say what one revolution is going to be? This is why it was quite a tricky question. One revolution, well, what we're going to do is we're going to take off a third of 1.5 to get to 1. So take off a third of 60, and what you'll do is you'll get to 40 seconds. So we're going to say every 40 seconds there's going to be a revolution of this Ferris wheel. So it will go up to its maximum and then it will return back down to its minimum. And because the whole thing needs to repeat 9 times to get to 360, because we know that after 40 seconds we're going to get to 1 revolution. So therefore, to get to 360 seconds, we're going to do 9 revolutions, which is 6 minutes. So in 360 seconds, we have 9 revolutions. But the question's not about 360 seconds, is it? It's about 720 seconds. So after 720 seconds, we're clearly going to have 18 revolutions, which is what we've talked about. So this is the one part of the mark scheme here I don't agree with, and I think there's been a slight typo here, because after 9 revolutions we get to 360, so after 18 we get to 720. So our domain is most logically going to be 720 seconds. So we need to correct this answer here so that we've got, rather than t being between 0 and 270, is going to be between 0 and 720. Now let's carry on with the second part of the question. So we've done A, B and C. We've already got our 11 marks, which is brilliant. So if we carry on with part D, by considering this graph, determine the length of time, state of time during 1 revolution of the Ferris wheel for which the chair is higher than the cowboy statue. So this is the big Tex statue. And it says it is 1.67 meters tall. Now, to me, this looks like we're potentially getting into the territory of trigonometry, potentially, but it might not be as complex as that. So what we want to have a look at is annotating this diagram with a little bit of a drawing. And we're going to say, well, how long is it bigger than 116.7, which is here? So what I'm going to do is I'm going to go back to my calculator. I am actually going to adjust my domain and range a little bit to match with what I decided earlier. So remember, we said the domain was going to be roughly 720. So if we go to our window, let's change our max to about 720. Graph. A little bit much going on. And actually we're talking about just one revolution. So I'm going to narrow this right down because we decided that one revolution is happening in a lot shorter amount of time. Let's now change this to roughly 50. Okay, and now we're going to add in a second line, which is going to be to do with the height of the big text statue, which is 16.7. So on our y equals, we're going to type in 16.7. We're going to type graph. And look, we're almost at a point where we can start to work this answer out. So I'm going to see where these graphs intersect. So we're going to press second calc. We're going to press number 5, and we're going to see where these two graphs intersect. It'll automatically jump from the first curve to the second curve and then on to the intersection. It intersects at 6.315. And remember, this is in seconds now, because the whole revolution happens in 40 seconds. So I am going to screenshot this for later. And let's see if we can remember this, 6.31. And we know that it's going to be higher than the big statue now beyond for this next section of the graph until it gets back down to this red line. So we're going to do the calc again. We're going to do the intersect, which is number 5. We are going to do the first curve, enter, second curve, enter, and then we're going to go on the curve, enter again. And we have now got a secondary value of x. We're going to come back to this image in a moment. We're going to take both of these values, and what we're going to do is a simple subtraction. So we've got the first value of 6.31 and the second value of 33. So all you have to do is subtract one from the other. You would do 33.6, 84039 minus 6.315. And the top tip is when you're putting this in your calculator, what we're going to make sure we're doing is we're not rounding it too early. So we have 33.684039 minus 6.3159613, and that would be our answer. Our answer would simply be 27.4 if we were to round it, because the whole revolution happens in 40 seconds, so that makes sense. Check your answer. Does it logically make sense? There is a plan to relocate this wheel onto a taller platform, which will increase the maximum height of the Ferris wheel to 65.2. So it's now being moved up the whole graph. So obviously everything else stays the same. It's just our D which moves the graph up and down. So previously our D was 30.9, I believe. Let's just double check that. Previously our D was going to be 33.6 because we decided we'd moved it 33.6 up. But now in this part of the question, we need to make sure it's much bigger than 33.6. Now I'm not sure whether I agree with this working out, but what I would do is I'd take the 33.6 value, which is our original D, and then we'd add the difference of the maximum in the previous question and the maximum in this question. So the maximum in the previous question was going to be 64.5, and then the maximum in this question is going to be 65.2. So that's just 0.7 different. So you take the old value of the d and you just add in 0.7. That's all you have to do. Very simple maths, which is 34.3. And we can see that this does agree with this answer, although I am unsure about this working out.